Picture this. You are on safari in Kruger National Park, South Africa. Your guide has stopped the vehicle near a waterhole because there is a lioness approximately 40 meters away doing the thing that lions do for approximately 20 hours out of every 24, which is to say, absolutely nothing. She is lying in the shade with the specific quality of relaxation that belongs to an animal that has no particular concerns about its position in the local food web. She is aware of the vehicle. She is aware of the people in the vehicle. She is making no movement toward either. Your guide turns the engine off. The lioness glances at the vehicle, returns to doing nothing. Your guide explains in the calm tone of someone who has done this hundreds of times and whose continued employment depends on nobody in the vehicle doing anything catastrophically stupid, that the lioness is not interested in you, that you can observe her from this distance without concern, that the key, the absolute essential rule is that nobody stands up suddenly, nobody makes any rapid movement, and under absolutely no circumstances does anybody get out of the vehicle and run. You ask, with what you hope sounds like academic curiosity rather than the sudden awareness of your own mortality that it actually is, what would happen if someone did run? The guide pauses, looks at the lioness, looks back at you, says, with the careful neutrality of someone choosing words that are simultaneously honest and not so alarming that they ruin the experience for everyone else in the vehicle. The outcome would be different. The lioness has not moved, but something about the scenario you have just been asked to imagine makes it feel like she is slightly more present in the conversation than she was 30 seconds ago. This scenario captures something that almost every person who has been in proximity to large predators has been told, and that very few people have had adequately explained to them. Why do predators attack when you run, and not, or at least not as reliably, when you stand still? Why does the act of running, which feels like the most instinctively correct response to danger, turn out to be precisely the thing that converts you from a large, potentially problematic organism that a predator is watching cautiously into a prey animal that the predator is now fully committed to pursuing? The answer reaches into predator neurology, prey detection systems, the evolutionary history of predator-prey relationships, the specific mechanics of how predators make hunting decisions, and the deeply counterintuitive reality that the most dangerous thing you can communicate to a predator is that you are afraid of it. And understanding that answer properly, not just as a survival tip, but as a window into the biological machinery underlying some of the most consequential interactions in the natural world, changes how you understand predators, how you understand prey, and how you understand your own nervous system's spectacularly unreliable advice in high-stakes situations. Start with the predator's decision-making system, because this is the foundation everything else rests on. Large predators, lions, tigers, leopards, bears, wolves, sharks, crocodiles are not making continuous active decisions to attack everything in their environment. If they were, they would spend every calorie they acquired on the energetic cost of constant hunting attempts and would be in a state of perpetual injury risk from the dangerous prey animals that most successful hunts require confronting at close range. Predators are instead performing continuous cost-benefit analysis on every potential prey encounter, assessing the probability of a successful outcome against the energy cost of the attempt and the injury risk of the confrontation, and conserving their hunting effort for situations where the analysis produces a favorable result. The variables in this calculation include the size and apparent physical capability of the potential prey, the distance between predator and prey, the terrain and environmental conditions that would affect the pursuit, the predator's own current energy state and injury status, and, critically, the behavioral signals that the potential prey is producing. Among those behavioral signals, movement is the most immediate, most powerful, and most difficult to misinterpret. A potential prey animal that is moving rapidly away from the predator is producing the single behavioral signal most reliably associated across the entire evolutionary history of predator-prey interaction with a prey animal that is frightened, that has assessed the situation as dangerous, and that is attempting to escape. That signal does not merely inform the predator that prey is present. It activates the predator's pursuit response at a neurological level that is below the threshold of deliberate decision-making. The pursuit response in predators is not a choice in the way that humans use the word choice. It is a triggered neurological program, a behavioral sequence that once activated runs with a momentum and urgency that overrides the more measured cost-benefit assessment that precedes it. The movement of fleeing prey activates visual motion detection systems that are specifically calibrated to the speed, pattern, and direction of prey animal escape movement, triggers the release of of neurochemicals associated with arousal and pursuit motivation, and initiates the coordinated physiological preparation for a high-speed chase, elevated heart rate, muscle activation, attention narrowing onto the fleeing target. This happens fast. In some predator species, the behavioral response to fleeing prey initiates within milliseconds of the movement being detected, before any deliberate assessment of the situation can occur. The evolutionary logic behind this rapid, somewhat automatic pursuit response is straightforward. In the ancestral predator environment, a prey animal that began running had almost always already assessed the situation as dangerous and was already moving at or near its maximum escape velocity. A predator that paused to carefully deliberate about whether to pursue was a predator that watched its meal disappear over the horizon while it was thinking about it. The predators that survived and reproduced in that environment were predators with pursuit responses fast enough and reliable enough to match the flight responses of their prey, and the result of millions of years of that selection pressure is a pursuit reflex that runs on a very short trigger, and that, once running, carries its own motivational momentum. Now examine the inverse. Why standing still works as well as it does, which is the part that feels most counterintuitive and most relevant to the safari scenario. The specific effectiveness of stillness in predator encounters depends on several overlapping mechanisms that together explain why a motionless human is a fundamentally different stimulus for a predator than a running human, even when the predator is fully aware that the motionless human is present. The visual systems of most large predators are specifically tuned for motion detection in ways that prioritize moving targets over stationary ones at the level of the visual cortex itself. Big cats, for example, have retinal architectures with high concentrations of motion-sensitive rod cells and visual cortex organization that is particularly efficient at processing movement-related visual information. In environments with complex visual backgrounds, grass, brush, dappled light, and forests, a stationary object that matches or partially matches the visual complexity of the background is much harder for the predator's motion detection-tuned visual system to lock onto than a moving object of equivalent size. Camouflage works by exploiting exactly this, disrupting the visual contrast that motion detection relies on, which is why motionless camouflaged animals are far harder to see than moving ones even when the camouflage is imperfect. For a human who is not camouflaged but who stops moving, this mechanism is less about becoming invisible and more about removing the visual signal that most powerfully activates the predator's pursuit response. The predator may be fully aware of the human's presence, maybe looking directly at them, but without the movement signal that activates pursuit, the encounter stays in the assessment phase rather than transitioning to the chase phase. The predator is deciding. And in the deciding phase, factors other than pure prey detection are operative. The predator's own risk assessment, the uncertainty about what exactly this large, unusual organism is, and how it would respond to a hunting attempt, and the fundamental predator conservatism about accepting unnecessary injury risk. Bears represent one of the most discussed and most counterintuitive cases of the standstill versus run dynamic, because bears are both large enough to be genuinely dangerous and common enough in certain human-occupied landscapes that encounters are not rare. The survival advice for encounters with grizzly bears, stand your ground, make yourself appear large, speak in a calm and steady voice, do not run, is so counterintuitive to the human instinct that it has to be explicitly taught and repeatedly reinforced, because the impulse to run from a large bear is essentially universal and essentially wrong. Bears are capable of running at speeds exceeding 50 kilometers per hour over short distances, which means a human running from a bear is a human who has communicated prey status and simultaneously removed any chance of outrunning the predator that has just been activated. The specific dynamic with grizzly bears is more nuanced than with pursuit predators like big cats, because grizzly bear aggression exists in distinct categories with different appropriate responses. A surprised grizzly that feels its space is being invaded is producing defensive aggression, for which the recommended response, playing dead, works by communicating that the threat the bear was responding to has been neutralized. A predatory grizzly that has identified a human as potential food is producing offensive aggression, for which the recommended response is active resistance, because submission in that context signals vulnerability rather than non-threat. Understanding which type of encounter you are in while a bear is moving toward you at considerable speed is the kind of cognitive challenge that makes bear country survival education considerably more complex than simple rules convey. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content, covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. The shark version of this dynamic has features that reflect the shark's very different sensory architecture. Great white sharks and other large shark species are not primarily visual hunters in the way that big cats are. They use a multimodal sensory system that integrates olfactory detection of dissolved chemicals in water, mechanoreceptive detection of pressure waves, and vibrations through the lateral line system, electroreceptive detection of the electrical fields produced by living organisms, and visual detection operating at relatively close range. The pursuit response in sharks is therefore triggered not exclusively by visual motion, but by the combination of sensory inputs that together indicate the presence of an injured or distressed animal. The combination of erratic movement, electrical field disturbance from muscular activity, and the water pressure waves generated by splashing and struggling, the sensory signature of an animal in distress, is what most powerfully activates shark investigative and pursuit behavior. A human swimming in controlled rhythmic strokes produces a sensory signature that is relatively unremarkable to shark sensory systems. A human thrashing and splashing in panic produces a sensory signature that closely resembles an injured or distressed animal, which is precisely the stimulus that shark feeding behavior evolved to respond to. The advice to swim calmly and directly towards shore in the event of a shark encounter is not about visual camouflage. It is about producing a sensory signature that does not activate the distress animal detection system that shark predatory behavior is built around. Wolves and wild dogs present an interesting variation on the flee response trigger because these are coursing predators. Predators that evolved to pursue prey over extended distances rather than using the ambush and short sprint strategy of big cats. For coursing predators, the assessment of whether a prey animal is worth pursuing involves not just the initial movement detection that triggers the chase impulse, but the ongoing evaluation of the prey animal's flight speed and endurance during the chase itself. Wolves pursuing a moose are continuously evaluating whether the moose is strong and healthy or whether it is showing signs of weakness, slowing down, losing coordination, demonstrating that the energetic cost of continued pursuit will eventually be justified by a prey animal that can no longer maintain its escape. Prey that appears strong and maintains its pace is more likely to be abandoned. Prey that shows weakness is more likely to be pursued to exhaustion. The implication for human-wolf encounters, which are genuinely rare but do occur in areas where wolf ranges and human activity overlap, is that the assessment the wolf is making is not only about whether you are moving, but about what your movement communicates about your capability. Confident, direct movement that does not communicate fear or weakness produces a different assessment than panicked, disorganized flight that communicates exactly the vulnerability profile that coursing predators evolved to identify and exploit. The crocodile presents arguably the most unforgiving version of the predator-encounter dynamic, because crocodilian ambush predation is initiated at distances so short and executes so rapidly that the window between encounter and attack is extremely compressed compared to encounters with terrestrial pursuit predators. Nile crocodiles and saltwater crocodiles approach prey through underwater concealment, achieving proximity before any surface visible detection is possible, and initiate the strike, which is explosive, covering several body lengths in less than a second from a position of already established proximity advantage. The advice to run in a zigzag pattern from a pursuing crocodile reflects the mechanics of crocodilian terrestrial locomotion, which is powerful but has turning radius limitations that a human running in irregular directions can sometimes exploit. The flight response is in this case more defensible than in big cat encounters precisely because the crocodile's terrestrial pursuit capability, unlike its aquatic capability, has real limitations that movement strategy can address. Mountain lions, cougars, bring the predator-encounter dynamic back to the ambush-predator context with a twist that makes the behavioral advice particularly important. Cougars are ambush predators that prefer to initiate attacks from behind and above. Their attack positioning preference is for the position that minimizes the prey's awareness and response time. Turning your back on a cougar, or crouching down to appear smaller, removes the face-to-face confrontation that the cougar is trying to avoid with its positioning strategy. The maintained eye contact, the facing toward the cougar, and the behavior of appearing large that survival guides recommend for cougar encounters are specifically effective because they deny the cougar the positional and perceptual advantage that its ambush strategy depends on. A cougar that cannot get behind or above its target, that faces an organism maintaining direct eye contact and presenting itself as large and confrontational, confrontational is a cougar that has lost its primary tactical advantage and that the cost-benefit assessment is now running against. The neurological experience on the human side of these encounters is worth examining directly, because the human response to predator presence, the physical experience of fear that predator encounters produce, is itself a product of millions of years of predator pressure on ancestral human populations, and is simultaneously very well designed and unreliable in important ways. The physiological fear response: elevated heart rate, adrenaline release, muscle activation, sensory sharpening, tunnel vision focusing on the threat, is the body's preparation for either fight or flight, and its evolutionary logic is impeccable. In an environment where the correct response to predator presence was often immediate, fast, decisive action, having a physiological system that prepared the body for that action before the conscious mind had fully processed the situation was a genuine survival advantage. The problem is that the flight component of the fight or flight response is what triggers the pursuit response in most large predators, making the body's default survival suggestion, run, the worst possible advice in most large predator encounter situations. The human nervous system evolved this response in environments where running sometimes worked, where terrain allowed escape that flat open ground does not, where social groups provided the kind of collective response that made individual flight less catastrophically isolating. In a modern encounter with a lion on flat ground, or a bear on a trail, or a shark in open water, the body's urgent recommendation to run is almost always wrong. The practical challenge this creates is profound, and explains why survival training for predator encounters focuses so extensively on override of the flight impulse, overriding a physiological response that is running at the intensity of it. Genuine predator encounter requires preparation, the deliberate establishment in advance of alternative behavioral programs that are available for deployment when the normal decision-making capacity is partially overwhelmed by the neurochemistry of acute fear. People who have been trained for predator encounters and who have rehearsed the counter-instinctive responses can access those responses under pressure in ways that people relying on intuition alone cannot. The deeper irony running through this entire topic is that the behavioral advice that predator encounter survival training converges on, stand your ground, maintain eye contact, appear large, project confidence, do not communicate fear, is fundamentally the same advice that applies to high-stakes confrontations in many human social contexts. The behavioral signals that communicate strength and capability to a predator assess essentially the same variables that behavioral signals communicate in human social hierarchies: size, confidence, willingness to engage, absence of the physical manifestations of fear. The predator is reading behavioral signals that were originally calibrated for the assessment of other predators and large prey, and the human who understands what those signals communicate can, with appropriate psychological preparation, produce the signal profile of something that is not worth attacking. The lioness at the waterhole never moved toward the safari vehicle because the vehicle and the people in it were producing a signal profile that did not activate the pursuit response: large, stationary, not communicating fear, occupying space with a quality of presence that did not resolve into the prey detection pattern that would have changed the calculation. If someone had jumped out and run, that calculation would have changed faster than the decision could have been reversed, and the guide's careful diplomatic phrasing about the outcome being different would have been understated in ways that became immediately apparent. The predator does not attack because it is evil, because it is waiting for an excuse, or because it has been watching you specifically and building up to a moment. The predator attacks when the behavioral signal profile of the potential prey resolves into the pattern that its nervous system is tuned to respond to, when movement communicates flight, when flight communicates prey, and when prey activates pursuit with the neurological momentum of a system refined across millions of years of evolutionary pressure. Remove the signal, change the profile, the calculation changes. The human who understands this has access to a kind of behavioral literacy with respect to predators that is, in its way, exactly the kind of knowledge that ancient humans accumulated and transmitted across generations of living in landscapes populated by animals that could and did eat them. The knowledge that stillness was safer than flight, that facing the threat was safer than running from it, that projecting capability was safer than communicating vulnerability. This was survival knowledge in the most literal sense, and it was knowledge that ancient human communities held with the seriousness that survival-relevant information deserves. We have the luxury of encountering it as interesting biology. They encountered it as the difference between coming home and not coming home.